Hello and welcome to this, the second module of lecture 2. So the content of this module will be mostly a little less abstract than what you've been doing so far, which is transfer functions and Laplace transforms, etc. Here we will look at something that is closer homes, such as electrical circuits, and how the tools that we've learned so far, that is Laplace transforms, they prove to be useful in solving for these variables like currents and voltages across elements and through elements of the circuits, right? And also to obtain transfer functions between voltage applied at one point in the circuit to the voltage obtained at the other point, at some other point in the circuit, or the voltage applied at some point in the circuit to the current through an element at some other point in the at some other part of the circuit, right? So these are transfer functions. In addition, you will also see that there are things such as current sources as well. So these are the duals of voltage sources. Mostly you're familiar with voltage sources, which are generally batteries. But suppose you have a very high value of voltage that is supplied, right? And also a very high value of load, a very high value of resistance in series with that voltage source. All right. Then if you apply small values of load resistance across such an unit, so for example, if you have, let's say, a voltage source which is, let's say, 500 volts, all right? So this 500 volts, and let's say you have 50 kilo ohms, all right? And you apply some load across this, load resistance across this, and let's say the load resistance varies between 10 ohms to 50 ohms. Then you can, for all practical purposes, consider that the current through this circuit or current across the load is more or less going to be constant. So such a setup can be considered to be the equivalent of a constant current source. Okay, current source, right? So we'll also see KCL and KVL. Mostly you're familiar with KVL when you have voltage sources and loops. So you apply mesh analysis and you derive the expressions for currents, right? But as a dual to that, excuse me, you also have Kirchhoff's current law, yeah, the KCL, which is useful when you have current sources in the circuit, mostly, right? You can also have voltage sources and you can still apply them. But yeah, when you have current sources, it's mostly useful. But before we move on to that, okay, let me stop the video. Before we move on to that, in the last module, I forgot to give you a certain number of exercises to try out. So these are 6 transfer functions. Don't worry, I'll just share these slides with you after the lecture. So you have these six transfer functions. Please try to obtain the inverse Laplace transforms of these transfer functions using the techniques that we've seen in the previous module. Okay. All right. Now let's get into a formal method or formal sort of an analysis of circuit. Okay. So how does a Laplace transform help us? Consider circuit elements such as resistances, inductances, and capacitances. Right? Now, if this is the direction of current flow, then the polarity, because these are not active elements, these are passive elements. So the polarities are taken to be like so. So the current enters through the positive terminal and leaves through the negative terminal. And the equations for these are given by V is equal to Ri, V is equal to L di dt, and V is equal to integration 1 over C 0 to T I dt, right? Now, as you might know already, if you've gone through the expressions for the properties of Laplace transforms, then this third one, the other ones are actually trivial. If you go into the Laplace domain, you find that Vs is equal to SL Is. Okay, this one will yield Vs is equal to R times Is, the static element. What about this? If you've gone through the Laplace transform table for for the integrals, you would know that this is given by 1 over s I of s c. Okay, why so? So again, take this up as an exercise. All right, you just have to use integration by parts in order to derive this. Okay, so you have to just take, let's say, what I'm asking you to show is essentially this integration 0 to t ft dt. All right, okay, let me just say f tau d tau dt e to the power minus st dt integration 0 minus to infinity. This is basically the Laplace transform of integration 0 to t f tau d tau. Right? So I invite you to derive this expression, all right, and see for yourself. So you take this as one part, you have this u dv, yeah. So you take this as u and this as dv. So you have integration u dv given by uv minus integration v dv. Yeah, just apply this and you should be able to derive this result here. Okay, so this is in general given by 1 over s f of s, where fs is the Laplace transform of the integral. Fs is the Laplace transform of, so fs is the Laplace transform of ft. Okay, so anyway, I've almost done this. You just have to fill in the steps in between, and that's your exercise. Okay, the point is that when you have these expressions in the time domain, by the same token, you can write the expressions in the Laplace domain as Vs is equal to Ris, okay, Vs is equal to Sl times Is, and Vs is equal to 1 by Sc times Is. So these terms, these are the equivalent impedances, okay, in the Laplace domain. So for all practical purposes hereafter, if you consider the equation, the differential equation in the time domain, you can replace it by impedances in the Laplace domain given like so, and then you can treat these integral differential equations that will arise in your RLC circuits. These can be replaced simply by impedance. Okay, so voltage is equal to, the voltage across a loop is equal to the sum of the voltage drops across the impedances in that loop. Yeah, the source voltage in a loop or in a mesh is equal to the sum of the voltage drops across the elements in that loop. Right? Now, as I just said in the while we were discussing in the previous slide, that it is customary or it is generally the convention that voltage is like the input, current is like the output, or you might at times take that voltage drop across a particular element, for which also you need to evaluate the current. So for example, if you want to find out the voltage drop across the inductance, and if you know the current, you just multiply it by SL and you get the voltage drop across the inductance, right? So typically the voltage is taken as the input and the current or some scaled factor thereof, or maybe some such function like this. So mainly the point is that you have to evaluate the current. Okay, so if you have evaluated the current, you can find out the output. All right. So for such cases, KVL proves to be useful. All right. On the other hand, if you had the current as the input, then the voltages could behave like the output. Yeah. SL and IS is equal to SC DS, right? So in that case, this 1 by R, 1 by SL, 1 by SC, these behave like what are known as admittances, right? So the impedances and the reciprocals, the admittances, right? So when you are doing KCL, on the other hand, that's when these admittances become crucial. Now, of course, these are certain things that you're familiar with. For example, if you have series circuits, sorry, that's actually the sign for parallel. So if you have series circuits, then if these are your impedances, okay, Z1, Z2, Zk, then the equivalent impedance, you know, is just nothing but summation Zi I is equal to 1 through K. All right. On the other hand, if you're considering the admittances, so Z1 is equal to 1 by Y1, right? So on till Zk is equal to 1 over Yk. So if you want to evaluate the equivalent admittance, yeah, then it's given by this expression. Okay, so these are some very trivial relations that you might already be aware of. So similarly, if you have parallel circuits, then you have Z1 like so, and then you have these, yeah, elements like these across connected across like these. And finally, you have Zk, right? So these are, suppose, the impedances. Then in the same vein, you can write this time the Y, the admittance equivalent is nothing but sum of the admittances. Yeah, these you should be able to see and derive for yourself. On the other hand, the equivalent impedance becomes nothing but 1 by Zi. I is equal to 1 through K. Okay. So of course, the equivalent admittance and the equivalent impedance are reciprocals of one another. All right. Right. The other important thing that you now need to know is how to convert a current source into an equivalent voltage source and the other way around. Okay. So suppose you have, so typically a non-ideal voltage source will have a voltage like so and a series. Let's not draw it like a resistance. It could be any general impedance. Okay. Right. So suppose you have an impedance like this, Z. Then by source transformation, it's equivalent. You can write this as a current source, okay, such that the flow of current is in this direction. And you have this Z here, okay, and where I is given by V by Z, okay. So if you're doing KVL, for example, yeah, if you're doing KVL, then this helps. But if you're trying to apply KCL to that same circuit, okay, if you're trying to apply KCL to that same circuit, it might help if you convert it to the equivalent current source like this. Okay, so these are source transformations. All right. Okay. Now let us discuss the very preliminary thing that you might be already familiar with, I'm sure, right? Which is an RLC series circuit. Okay. And we shall see how whatever we know about Laplace transforms, etc., they prove to be useful in this case. Okay. So suppose you have a voltage source given like this. This is, let's say, V in. All right. So then, using the ideas that we've just propounded, I can replace this in this fashion. And then writing this equation becomes quite straightforward, isn't it? So I can write I of S times R plus 1 by SC plus SL is equal to E in of S. Okay. which would in turn lead to an expression given by check CS over LCS squared plus RCS plus 1 is equal to, this is I of S over V in of S. Right? Okay. So if you now simplify a bit, I think the expression would be I of S over V in of S given by 1 over L divided by S square plus R by LS plus 1 over LC. All right. So now suppose R is negligibly small. Okay. In a moment, it will be clear why I'm making this assumption, because I want to give you a practice for Laplace transform. Additionally, consider V in S is equal to 1 over S, which just means that it's a step input. Okay, so this is basically a constant voltage applied at t is equal to 0, like a DC. All right. Okay, then what would the current be like? What would the current look like? Yeah. So, okay. Now let's see. Therefore, we have I of S is equal to, so one of these SS, 1 by S will cancel out with this S in the numerator, right? This particular S, because the step input V in is 1 by S, so it cancels out, right? So please check that this will indeed turn out to be I think I missed an S somewhere here. Yeah. So in this expression, I actually missed an S here. This will actually be S by L. Right. That's why I was a little perplexed about this expression. Right. So now we have the expression. Yeah. So now we have the expression given by 1 over L upon S square plus R by LS plus 1 by LC. Now the fact that R is very small tells you, okay, that the roots of this quadratic equation, yeah, just ask yourself why. I'll not, this is a mental thought exercise for you. If R is very small, the roots of this particular polynomial will be complex, okay. So in that case, what would IT be? It is the Laplace inverse of IS is equal to the Laplace inverse of 1 over L upon S square plus R by LS plus 1 over LC. Right? Yeah. So now we just use the techniques that we've learned so far. So IT is equal to Laplace inverse of, let's just play around with the denominator first. So we complete squares, S plus R by 2L, I think that's what it is. Yeah. Plus, yeah, exactly. Now we have this root over of 1 by LC minus R squared by 4L squared. Yeah. So now you see that it can be written in this form with having complex roots because R is small. So that is why I wanted to make this assumption initially. Okay. And in the numerator, so why am I trying to get it in this form? Because this is a form that I am familiar with in the Laplace domain, right? So let's say I also write O1 over LC minus R squared by 4L squared, and then I'll have to adjust this. So I'll have to adjust this. I'll have to adjust this with this expression. 1 over LC minus R squared by 4L squared. Again, I'll not do all the steps, but I'll just leave it to you as an exercise to see that this expression turns out to be, I hope I'm not making a mistake here. Yeah, I think it will be, yeah, L by C minus R squared over, yeah, I think it will be just R squared. Yeah, yeah, that's it. It's just L by C minus R squared times e to the power minus RT by 2L sine of 1 by LC minus R squared by 4L squared times T. Yeah. So this is going to be the current. Okay. Now, as you might see, as T tends to infinity, this will decay to 0. So that's because physically you can see that the capacitor, the charge builds up across the capacitance, and once that has happened, once the entire charge has built up, this capacitor will behave like an open circuit. Yeah, that's what happens at steady state with capacitances. Capacitances behave as open circuits, inductors behave as short circuits. So you take an RL circuit, apply similar technique, it will be a first order differential equation, which you can treat with this in the same fashion as you treat with Laplace transforms. So I urge you to take those as exercises as well and verify for yourself. You might apply final value theorem also. You know, when you apply a DC voltage, that Laplace transform the voltage is 1 by S, just like we've chosen here. Okay, but I would suggest that even without applying the final value theorem, just derive this expression in the time domain using inverse Laplace that you've just learned, and see for yourself that in an RL circuit, the L behaves like an open circuit, and at steady state, the value of the current is V by R. And in a capacitive circuit, the RC circuit, on the other hand, at steady state, the current is 0, with the capacitance behaving like an open circuit element. Okay, so those are your exercises. Okay. Study RL and RC circuits with respect to their responses to a constant voltage. All right. Okay. So I think at least now you're beginning to see some of the utilities of this particular Laplace transform that we've learned. All right. But this is a very sort of simplistic and trivial example where, you know, you could have even solved this. It's a second order differential equation after all. Okay. But where things start to get really complicated are when you have multiple loops in the circuit. Okay. And that's where you will see the merit of this Laplace transform method, because of this Laplace transform method, and by considering each circuit element and replacing them by their equivalences in Laplace domain, the equivalent impedances in Laplace domain, the analysis becomes really smooth. Okay, it becomes really easy. So let us consider this. So this is 1 Henry. That's the inductance. All right. Then you have this 1 ohm. This is a 1 ohm. All right. And this is again 1 Henry. And this is 1 Henry. Okay. So here the exercise is that given a source like this, so we're not saying that it's basically a constant voltage or whatever, it could be any voltage. So this is your output voltage, okay, V out. So it is asked that find V out of S over V of S, okay, obtain this. Now clearly this cannot be simplified using any series parallel combination or those sort of techniques, right? I mean, it's not that simple. So here you go for mesh analysis, okay. So you consider this to be current as I1, this as, let's say, I2, and this as I3, okay. So I will go through the trouble of actually writing these equations. So you replace 1 Henry by just S, replace 1 ohm by just 1, all right, because SL is just S into 1, yeah. And now we can write these mesh equations. So what happens for the first loop, first mesh, you have V of S is equal to I1 S minus I2 S times S. There is this inductance. All right. That is the voltage drop. So this is the direction of voltage drop. So you're taking this as the direction of voltage drop while considering this loop. And while considering this, again, we are considering this as the direction of voltage drop. So this must be balanced, right? So this is negative to positive here. So this applied voltage must be balanced by the voltage drops across the elements. So the second element is just a 1 ohm. So it is just, we are adding this plus. So it's like force balance, you know. Like D'Alembert's principle we apply. So here also, this is now I1 of S minus I3 of S. All right, that's equation number 1. The second loop, if you consider, there is no external applied force or voltage here. So it's going to be 0. All right. And what you can now write is, for this resistance, the voltage drop is, now we are considering this to be the direction of flow. So it is I2 minus I1, I3, I'm sorry. So I'm dropping the S for brevity's sake. When I'm writing in capital letters, you might assume that it's basically the Laplace domain that I'm dealing with. Plus, through this inductor, again, this is the direction of current flow. This is positive terminal, this is the negative terminal. So you can write as S times I3 only, okay? Plus, this is the third element. Again, that is an S times the flow of current. I2 is in this direction, but remember we had considered I1 in this direction. So now we have to write I2 minus I1. So by simplifying, we can write this as minus S I1 plus S sorry, is this should be I2, no? Yeah, this is I2, not I3. So this is S plus 2 I2 minus I3 is equal to 0. So this equation also I would like to simplify in the same fashion. So I can write this as S plus 1 I1 minus S I2 minus I3. Okay, and by writing in the third loop now, so again, if you simplify, you'll find that in the same manner as we've written here, excuse me, we might write this as minus I1 minus I2 plus S plus 2 I3. Okay, so this is equation 1, this is equation 2, and this is equation 3. All right. So having written down this equation, you can begin to notice the pattern here. The pattern is very simple. If you're considering your loop variables in such a fashion, your loop currents in this fashion, you can now straight away, even without application of much thought, you can write this in a very simple manner. How so? Just consider the applied voltage or the applied external forcing function on the left hand side of the equality. So for one loop, there is So you might have had some voltages here also. In that case, these wouldn't have been zeros. In this case, it turns out that there is only a single voltage source, so it's just appearing in one equation. Okay. On the right hand side, that is on this side, you're going to balance out the voltage drops across the elements. So instead of considering these equations, a straightforward way to see this is the loop variable corresponding to that loop will have as its coefficient the sum of all the impedances in series in that loop. Okay, so for example, in this loop it is S plus 1. So S plus 1 becomes the coefficient of, sorry, that's I1. Okay, you observe in the second loop, it's I2. So the overall series impedance in the loop 2 is S plus 1, that's 2S plus 1. Okay, I think I messed this up. Yeah, I have messed this up because I had initially not did this. Yeah, sorry. See, that actually brings to attention this mistake I had made. This way you can never go wrong. So I'm glad I made that mistake because that just illustrates the point that there is a shortcut. Okay, so it's just 2S plus 1 times I2. Now similarly, when you're going for the third loop, you have S plus 1 plus 1, that's S plus 2. So S plus 2 appearing as a coefficient of I3. What about the coefficients of the non-diagonal entries? That is, the diagonal entries for loop 1 is I1, the diagonal entry for loop 2 is corresponding to I2, and the diagonal entry for loop 3 is corresponding to I3. So that's how you evaluate them. Straight away, take the impedances in series and sum them up. Yeah. What about the other ones? So is this loop sharing any particular element with any other loop? So for example, loop 1 is sharing this resistance with loop 3. So therefore, whatever is the impedance of this particular edge or this particular element, okay, whatever is the impedance of this particular element, it will appear as the coefficient of the loop variable of that loop with which it is being shared. So loop 1 and loop 3 are sharing this 1 ohm resistance whose impedance is 1. So this will appear with a negative sign as the coefficient of I3, which is the loop variable for loop 3. Similarly, look at loop 2. Loop 2 has a current I2, and the element shared between loop 1 and loop 2 is this inductance, whose impedance is just S, right? So that S with a negative sign appears as the coefficient of the loop variable of loop 2, that is I2. You exactly observe the same pattern everywhere. So now you don't even need to bother about writing these in a careful fashion in two lines. Anytime you encounter a circuit like this, on the left hand side, just write the externally applied voltage or current source, voltage source in this case. Yeah. And on the right hand side, you can just apply this technique. Okay. So for the loop variable for that particular loop, it is the sum of the impedances across the loop. And for the cross terms, for the other terms, it is just the impedance that is common to, that is overlapping between the given loop and the loop with which the other current is associated. Okay. So now, of course, you know Cramer's rule, right? So this is basically, you can treat this exactly the way you do with simple numbers. Okay. So now you can use Cramer's rule to solve for I1, I2, and I3. Now, in this particular case, I don't even need to solve for I1 and I3 because as soon as I have solved for I2, I can just multiply it by an S and I would exactly know what the voltage drop across this element is, which is basically the output that I have to evaluate. All right. So what I will do is I will first write down the determinant of the system, S plus 1 minus S minus 1. The second one is minus S, 2S plus 1, minus 1. Last one is minus 1, minus 1, S plus 2. This is the determinant. And I leave it to you as an exercise again to simplify and check that this turns out to be S into S square plus 5S plus 2. Okay, this is an exercise. Of course, this is a very trivial exercise for you. All right. So in order to solve for I3, you need to replace this column. You need to replace this column by VS 0, 0. Yeah, that's how you solve. So this is on the one side of the equation. Okay, AX is equal to B form, so this is the B, right? So if you solve that, you will find that that other determinant turns out to be, okay, I think it turns out to be s squared plus 2s plus 1. Yeah. So that other determinant, if you replace this with this, then that determinant turns out to be this. So therefore, I2s over Bs is given by, yeah, the expression is s square plus 2s plus 1 upon s into s square plus 5s plus 2. So now if you want to find out V out S, just multiply this by S. So therefore V out upon V in, that is a transfer function, that will just be nothing but S squared plus 2S plus 1 upon S squared plus 5S plus 2. Alright? Right. Great. So we have seen that. This is how you solve it. But this is using the conventional mesh analysis. So we will do the node analysis for the same circuit. Okay? And we'll write down the equations. So again, you have the luxury of referring back to this circuit. So that's why I have drawn it in a piece of paper so that I can write the equations. Okay? So how do you, no, I think I'll have to draw the circuit again. Never mind. Okay. So for that same circuit, now we want to do a node analysis using KCL. So how do we go about that? Yeah. Okay. So this is V in or whatever, and this is V out. Okay. So for this case, you have to focus on certain nodes. So what are these nodes going to be? Call this node 1, call this, okay, okay, call this node 2 and call this node 3. The question is, how do you know? You know, these loops are very obvious to identify, okay? Loop 1, loop 2, and loop 3. It was very straightforward that way. So how do you know that these are the nodes that will suffice? Yeah. So in this case, of course, it is not a big question. You just see that all these nodes are common. One end of these elements are basically connected at the same node. So this is basically the datum. Okay. So you can consider this to be the all right. In other cases, when you're trying to do this sort of an analysis, so remember, this is a very important point. For application of KVL, all right, you can merge together elements in series. What I mean by that is, see here, for instance, if I had, instead of this 1, if I had a resistance and another say inductance in series, I do not need to consider them as separate units. I could have just called the whole impedance as 1 plus S and replaced this here. All right? Because when I am doing KVL, the variable that I am interested in evaluating is a current. And currents through series elements are same. Right? Currents through series elements are the same. So therefore, I can merge them together without any sort of problems. But on the other hand, if I had this one, of course, even then you can sort of find out the equivalent impedance, but it's not a very good idea. If you had say some element in parallel with this, okay, you could have considered an additional loop here, all right, to accommodate that. So if instead of having it being in series, if this inductance of 1 Henry, there was another inductance of 1 Henry in parallel with this 1 ohm, you could have considered that as an additional loop. Very simple equation of the loop though, but anyway, you could have considered that, right? In the same manner, when you are considering for application of KCL, you can merge together elements in parallel. Okay, why so? Because when you're doing KCL, basically your quantities being evaluated are voltages. You'll call these voltages. So you'll call this, let's say V1, V2, these node voltages V3. So when you have parallel elements, for example, if you had, say for instance, a resistance in parallel with this, for the purpose of this particular terminal, this particular node here, the voltage drop would have been identical. Yeah. So you could have merged them together, these parallel entries. Okay. And we'll see that in this KCL analysis, just like in the KVL analysis, we considered impedances. In the KCL analysis, we'll similarly consider admittances. Okay. So I'll write these equations. And again, I'll not go through the entire details, but I'll leave it to you to check that, again, you'll have to use Cramer's rule and determinants and things like that. But I'll just write the equations for you. So for example, here, the first equation would be, if you're considering node 1, okay. So node 1, what is the voltage at node 1? So node 1's voltage is nothing but voltage is equal to Vn. That is the first equation. So there is no point in trying to evaluate what is V1. V1 is already Vin, right? So the voltage at the first node is known. What is the voltage at the second node? It's V2, right? So now equating the KCL. So the sum of the incoming currents to this should be 0. So V2 minus V1 upon 1. That is the 1 ohm resistance. Plus V2 minus V3 upon 1. Plus, what is this? We are considering this the datum, so this is 0 volts, right? Reference. Plus V2 minus 0, so I'm not writing that, upon SL. What is 1 upon SL? 1 upon SL is nothing but the admittance offered by an inductor. Yeah? So this is equal to 0. So because there is no current source which is injecting current into this node, therefore this is 0. If you had a current source, on the other hand, there are several such nice problems in the book by Norman Nice. I advise you to go through them. So if you had a current source which was pumping in current, then on the right hand side you would have had some non-zero. Alright? Right. What about this is the second equation. What about the third node? Now for the third node, V3 upon SL. So L is again 1. So why am I writing L separately? I already said it's 1 Henry. So no point in writing that. Okay. V3 by S plus V3 minus V2. Again, I'm dropping the SS here. These are all in Laplace domain. V3 minus V2 upon 1 plus V3 minus V1 upon S is equal to 0. Again, you will begin to see some pattern here. So what is the pattern here? You see, the pattern that begins to emerge is, of course, in the first one you will not see any pattern. The first one is just a given. In the second one, which is node 2, whose corresponding variable, associated variable is the voltage 2. Alright, so what is the coefficient of V2? The coefficient of V2 turns out to be 1 over 1 plus 1 over 1 plus 1 over S. You might think, what is this daft way of writing? But there's a reason why I'm writing this. So 1 over 1 is the reciprocal of the resistance, which is the conductance. This is again the reciprocal of the resistance, and this is the reciprocal of the inductance or the impedance posed by the inductance. All right. So what is this? This is the net sum total of the admittances that are incident on this node. Okay, so all the admittances that are incident on this node, they are summed up together like a parallel combination. Okay, they are summed up together and they become the coefficient of this node variable. Okay, what about the coefficient of V1 in this? So because V2 and V1 share this element, there's an element, that's an edge connecting. So in graph theoretic terms, again, let's not bother too much, but these are nodes and these can be represented as edges. So if there is a connecting element between these two nodes, then the admittance posed by that connecting element with a negative sign will appear as the coefficient of that variable. So with V1, what appears here? Just a 1 by 1. Similarly, with V3, you see just a 1 by 1. Okay. So again, of course, this is not something that you have practiced too often probably, because you are most familiar with the voltage source and the KVL analysis. But I urge you to investigate, and also I hope that this will convince you that this is exactly the dual of the other. So similarly, if I can now blindly look at this, see, I don't even need to look at this equation. I'll not look at that. I'll just blindly look at this. So this is V3. So what is the overall 1 over S plus 1 over S plus 1 over 1? What are the other nodes that are connected to V3? Both V1 and V2. Okay. So what is the admittance of this? This is just 1 over 1. So minus 1 over 1 will be the coefficient of V2. Okay. And what is the connecting admittance of this connecting element with V1? It is 1 by S. So I just said minus 1 by S, V1 is equal to 0. So therein you have your three equations. Again, please apply Cramer's rule as before as an exercise and find out. So here obviously the way you have defined V3 is V out. So find out, verify that indeed the transfer function that we obtained here is identical to the one that we obtained by this KCL. Okay. So that is an exercise for you. So I leave that as an exercise for you. Verify the TF using KCL. Okay. All right. But every now and then, once in a while, life becomes more complicated. Okay. So everything may not be as simple as this. Okay. These are loops. So you'll see mostly in Norman Nice's book, they consider mostly these sort of examples. Okay. But what if life throws bigger challenges at you? So for example, we have something like a twin T circuit. Okay, forget about the name, don't bother too much with the name, just try and see what it looks like. Okay, so this is how it will look. Yeah. All right. I think, yeah, let's call it identical C1 here. Okay, so far so good. We have R, I think, yeah, this is R1, all right, and this is also R1, yeah, and this is C2, like this. So far it seems like a very standard circuit, right? I mean, we should be able to easily obtain any transfer function between any variable, any current and any voltage at any part of the circuit. Just a little bit of patience and careful calculation. But now, just to make life a little difficult, not very difficult, but a little difficult, what we will do here is, we will additionally have this, okay, call this R2. So basically it's a T network. One T is this two capacitances with a resistance, and the other T is two resistances and a capacitance. Okay. Now, an immediate glance at this will tell you that, you know, of course you can write loop and mesh currents and things like that, but as this circuit looks, it looks a little cumbersome. So can we simplify this? Can we make life a little easier? That is the question. It turns out that there is, again, I do not want to use these graph theoretic terms, because these are supposed to be done in detail in a course on circuit theory. But just to show you that this can be applied, you consider these elements and you consider these nodes, okay? So consider the node, the two nodes corresponding to every element, okay? So these are all the same node, yeah? They're equipotential, okay? So how many such nodes can you find here, right? These are again the same node. So I just, let's say I just name them in this fashion. So I call this node as node 1. Both of these are node 1, okay? And I call this one as node 2, call this one as node 3, and call this one as node 4, okay? And then what I do is, and call this as the ground, so maybe call that node 0, all right? And once I have done this, I urge you to verify that this is indeed the case, that this can be represented in this fashion, yeah, without any harm. Okay, so let's call this the node 0. I'm just getting from this circuit to this transformation here, all right? So let's call this 3, let's call this 4, call this 1, let's call this 2. Okay, and let me name these currents. So what is this element going to represent? 1 and 2. Between 1 and 2, you can see this is going to be R1. Between 2 and 3, again this is going to be R1. Between 3 and 0, what is the okay, I think I missed something here. Yeah, so between 3 and 0 there is supposed to be the load. This is the load resistance, okay? Between 3 and 0, this is going to be RL. Between 2 and 0, you can see this is just the capacitance. Between 0 and 4, you have R2. Between 1 and 4, we have C1, and between 4 and 3, you have C1 again, right? So you can now clearly see the T structures here, right? R1, R1, C2, C1, C1, R2, and then this load here, right? And between 0 and 1, you have the voltage source. So this is the V in. Now, once you have written this, yeah, once you have written it in this fashion, now it is easy to see that if you consider these loops meshes here and call this as loop 1 current I1, okay, or call this as loop 2 current I2, this is loop 3 current I3, and this is loop 4 current I4. You can again write down the KVL here. By the same token, you can also consider the currents flowing through these elements and use KCL. So if you're considering these loop currents, you'll be using KVL. If you're considering this, then you'll be considering KCL. So basically, assign voltages to these nodes. So call this V2, V1, V4, V3. So basically V2 minus V1. So the way it is written here, it is very easy to use KCL here. Of course, you can also use KVL. But the point I'm trying to make here is that when circuits look a little more complicated, okay, it often helps to draw out a planar graph such as this, which then makes it easier for you to see the circuit in a new light. And then you can again apply the standard techniques of KCL and KVL that you are so familiar with. All right. So having done that, before you move on to the next module, please look at these two. Okay. Again, once again, I'll be sharing the slides. So these two problems. Okay. So this is the current source here, IT. All right. So apply KCL and write down the equations. If you've written down the equations, I'm sure you'll be able to use Cramer's rule to solve. That you're very adept at. So the main idea of this practice is to gain familiarity with writing these equations without much trouble. So again, here you might have to probably use some graph, okay? Because whenever you have these loops, yeah, these sort of structures, this one wire looping over the other, you might have to simplify things by drawing a planar graph that is equivalent to the given circuit, okay? So that will give you some practice. So please attempt these two, and we end module 2 here. Module 2 will be a shortish sort of a module. We'll see you at the end of the break. Please attempt these along with the other exercises that I've given you already. Okay. Thank you very much.